Okay. Welcome, everybody. I'm Andy Miller. Most of the people in the room know me. I'm a professor in the Department of Geography and Environmental Systems, and I am responsible for organizing the seminar series. So welcome to our first seminar of the fall 2023 semester. We're very pleased to have our speaker here with us in person. We will have a mix of in-person and virtual seminars this semester. Before we get going, I just want to call your attention. I did send an email about this out a little earlier today. So I just want to point out that the title of my email today was From a Summer of Fire and Smoke to a Fall of Seminars about Fire and Smoke. So this is the first one. There's actually a presentation being given by the Cary Institute of Ecosystem Studies tonight at 7 p.m. I can't go to it because I have another meeting, but it's about adapting to the new age of wildfire. And there is a link in person or live stream. So if you go to that email, you're just watching that tonight, you can do that. And then 2 weeks from today, at not our normal time, but at 11 a.m., there will be a seminar sponsored by the physics department here. It'll be in 401 in the physics building, and I'll send out an announcement about that. They did ask us to go-sponsor. That's 11 a.m., and that is about pyrocumulus clouds. Who knows what a pyrocumulus cloud is? You do know what is it?
You told us.
Oh, right.
It's like when fires get big enough, they create their own weather system.
Yes. So it's essentially a fire tornado. Pretty scary. Anyway, I'm going to turn it over to, I have to switch this back to your animation so we can, okay, I'm going to turn it over to Samantha, who will do the introduction, and then our speaker will take the helm.
Thank you all for coming. Mark Gibson is a senior project scientist with KCI in Sparks, Maryland, and has over 20 years of experience conducting air quality and air compliance projects while in the United Kingdom, Canada, and since 2019, the United States. Prior to moving to the US, Mark was an associate professor of environmental engineering and director of the atmospheric forensics research group at Dalhousie University in Halifax, Nova Scotia, Canada. And between 2015 and 2020, Mark was also a NASA project scientist at the North Atlantic Aerosols and Marine Ecosystem Study. So, Mark, essentially.
Very good. Thank you, Samantha. Good afternoon, everybody. As Samantha mentioned, I used to be a professor at Dalhousie University, and that's where I did the research that I'll be presenting. So I thought I'd give this talk, given we had the wildfire smoke drifting down over the region, and this talk is very much involved with that. So I thought I would volunteer to give a talk on wildfire smoke. Okay. So as way of background, boreal forest fires typically burn on average 2.3 million hectares of Canadian wildland annually. But by September 2023, wildfires have been estimated to have burned approximately 17 million hectares. That's the worst in Canadian recorded history. And of course, the heat and climate change is exacerbating this. The heat is causing the wildfire season to start earlier and to last longer. And the heat is exacerbating the fires themselves, creating fire whirls and fire tornadoes and the pyrocumulus clouds and so on. So these biomass burning events, they're a significant primary source of health and climate relevant particulate matter and gases. And the wildfire smoke undergoes complex chemical transformations en route down to downwind receptors. And a receptor could be a town, a city, even a region. So the formation of ground level ozone, for example, and secondary particulate matter. So ground level ozone is a powerful greenhouse gas in its own right. It's also a powerful air pollutant. I'm going to be talking a lot about PM 2.5, so some of you may not know what that is, and that is particulate matter with a median aerodynamic diameter of 2.5 microns or less, and it's 20 times smaller than the diameter of a human hair, and you can't see it with the naked eye, but you can see the effects in the atmosphere because it scatters sunlight and it creates that haze that we saw back in June. The particles are so small you can breathe them deep into the lung, into the alveoli, where they can cause diseases in situ. but it can also pass into the bloodstream, lymphatic system, and also into the nervous system, where it can cause diseases elsewhere in the body. As you can see from this slide, there are a complex mixture of liquids and solid particles. There'll be soluble material in there, and you can see that that's black carbon from either diesel emissions, could be wood smoke as well. And black carbon is full of carcinogenic material, and its surface is very irritating. So it's very irritating to the lining of the lung. So there are many different anthropogenic sources and many natural sources. There's chemical species, there's biological components. So COVID would be classed as a PM2.5 particle. And the shape is very important. The morphology can alter the environmental interactions and impacts. But in terms of health, if you think of asbestos, it looks like balls of fish hooks. So the morphology is incredibly important in terms of how it affects the lung and the body at large. Okay, I just want to put air pollution and health into context. So it's quite incredible to imagine that 4.2 million people die of outdoor air pollution every year. And depending on the study, it's estimated between 60 and 200,000 Americans die from air pollution every year. And that's on a par with road traffic accidents in the US. Of course, wildfire smoke is a contributor to outdoor air pollution and indoor air pollution. I'll talk a little bit more about that later. So the typical short-term health effects from air pollution, you get reduced lung function. So if you do a little test with a spirometer and you blow into it, after a while when you're being exposed to the wood smoke, that lung function will reduce. You can get irritation of the eyes, nose, mouth, and throat. You can get asthma attacks caused by exposure to the wood smoke. And also there's evidence now that air pollution causes asthma. There's been a few studies in Europe.
I just realized I should have turned on the video camera so you can be visible on the screen. Could I just interrupt you?
You certainly can, yes.
I don't want to have a whole seminar go by and nobody who watches the recording can
Got a
see the
better face
speaker.
for radio.
Let me just do that real quick. Sorry, folks, for the interruption. Whoops, that's not, okay. Stop sharing, turn on the video. Okay, and now we'll go to, we will share screen again, and you should be visible. Oops, I turned off the video. Okay. I'm not seeing you. I'm not seeing the video here. All right. Sorry, I don't want to wreck the seminar. So
Okay.
I was hoping to have you on screen.
All right, thanks.
Certainly then, I should have thought about that before.
No problem. So there's other health effects. These include coughing and wheezing, activities reduced and reduced energy level, increased use of medication. So you can see there's increased sales of asthma inhalers during air pollution events. Increased hospital admissions for strokes and heart attacks. And particulate matter causes inflammation in the lung and the bloodstream, and can cause clotting in the brain. Also makes the blood sticky, so the heart has to pump harder, so that can increase heart attacks. And there's increased evidence now of potential link between PM2.5 exposure and dementia. Of course, firefighters are exposed to an acute concentration of PM2.5 and toxic gases. And this can cause acute and chronic health effects. And it's saying here that the agencies have done little to protect their workers, so that's quite alarming. Okay, so let's look at the emissions in a little more detail. So these are the cumulative daily total wildfire carbon emissions for Canada. And the dashed gray lines are the emissions for the last 20 years, and the black line is the average. And you can see the red line for 2023, and it's about 3 times the average, and it shows no signs of stopping anytime soon. So that's the total wildfire emissions in megatons of carbon. And incidentally, if you multiply the y-axis by 3.67, you get the emissions for CO2 equivalents. Okay, so what tools do we have to find the location of forest fires, wildfires, and how do we track their evolution in time? And this is an animation of 19 weeks of the Canadian radiative power, beginning from May onwards using the NASA MODIS satellite. Okay, and if you look at the June concentrations, you can see the levels in Quebec should just disappeared, but and then we get the concentrations up around Great Slave Lake, and there was Yellowknife. You probably saw on the news that Yellowknife was evacuated because of the wildfires there. Then in British Columbia as well, there was evacuation. So there's the wildfires that cause all the smoke to come down over New York and this region as well. So this is a really powerful tool for locating the fires and seeing their evolution in time.
Sorry, I went to the other one. So I should have left it. There you are.
There we go.
So if we want to go back to this one like that, okay, there you are.
Great, thanks, Andy. So this is a product that the government of Canada has produced, and it's a forecast model, 3-day forecast model from now, and it's the wildfire contribution to surface PM 2.5. So you can see the red areas, the very dark areas, that's the source of the fire. Then you can see the dispersion over the next 3 days. And this is really useful for public health advisory. So if they want to put out an air quality alert for fire smoke, wood smoke that's coming down in the next couple of days. So this is a very useful product. So there are other tools as well. This is an animation that shows the analysis based on the assimilation of satellite observations of organic matter aerosol optical depth. That's just the absorption of the sunlight by the particles. So the darker it is, basically there's more sunlight being absorbed by the particles in the air. So if we get to one of the salient features, of course, of this is you can see that the wildfire smoke, it travels great distances. So the fires in North America can travel right across to Europe. There's the smoke in Great Slave Lake around Yellowknife there. Yeah. And then we'll have the smoke from Quebec fires coming up in June. Here we go. There's the fires, and there's that plume that came down and caused that haze, 6th, 7th, and 8th of June. And talking of Yellowknife, during the fire event that was surrounding the city, the Canadian Air Quality Health Index, this is similar to the Air Quality Index here, was 11. So that's extremely unhealthy air. And in terms of environmental justice, if you have housing stock which has forced air systems and particulate filters in, it can scrub out the wildfire smoke. But in housing stock that doesn't, and it's usually the disadvantaged population, they don't have forced air, they don't have particulate filters, and that smoke can fumigate indoors very, very quickly. I've done some work on residential wood smoke with that regard. Okay, I just want to look at the event that happened on the 6th, 7th, and 8th of June in a bit more detail. So here's fire information for resource management system. This is FIRMS. This is one of their MODIS satellite images, again showing the wildfires in Quebec on the 5th of June. And then what we can use is a NOAA product called High Split, and this is an air mass back trajectory. So it goes back in time, that's 24 hours, 4872. So it's a 3-day air mass back trajectory. What it's showing us is the air mass where it traveled en route to the receptor, and I put New York as the receptor in this instance. So you can see clearly that the air mass passed through Quebec on the 5th and 6th before reaching New York. So that gives you evidence that it's picking up that wildfire smoke in that air mass and bringing it down to New York. And on the bottom panel here, you can see that air mass didn't rise up very high in the atmosphere. So the wildfire smoke wouldn't have dispersed vertically so much before it reached the New York. So that's 500 meters above ground level. And you can also use true color satellite images as well. Again, you can see the fires and then you can see the smoke. And then with other images, you can see the smoke passing down to New York and this region. Okay, so it just so happened that KCI were monitoring total suspended particles downtown in Baltimore. And, TSP actually has PM 2.5 within it. So it's total suspended particles in every size fraction below. So PM 2.5 is part of that composition. So we can see the typical concentrations before June the 6th, bouncing around 12 micrograms per meter cube. And the national ambient air quality standard is 35 micrograms per meter cube over a 24-hour period. So we're well below that. But then on the 6th of June, we get a spike over the standard. And then on the 7th of June, we get that big spike of the wood smoke coming in. And that was up at around 130 micrograms per meter cube. And to put that into context, that's similar to what you see in a big city like Beijing or Mumbai. So, and as you saw, you could see it, you could even taste it. Okay. And then the next day got even worse. So we just so happened we have a particulate monitor at work. So I rushed outside with that instrument, and the units are in milligrams per meter cube. So that is 302 micrograms. Remember, the standard is 35, so we're nearly 10 times greater than the national ambient standard. And we were inhaling this. I think this is the worst, apart from sitting at a campfire, I think this is the worst air quality we've probably all ever experienced. Okay, and then I was curious, did that outdoor air pollution infiltrate inside? Now, at our offices, we've got very good particulate filtration, so it should scrub it all out. So this is the indoors, and we've got a concentration of 26 micrograms per meter cube. Now, typically, the air in this room is probably around 2 to 5 micrograms per meter cube with the forced air filtration. So you can see, even with the filtration, we're still getting some of that wildfire smoke infiltrating indoors. Okay, so that was a bit of background on the health effects, some of the tools you can use, and some of the measurements that we made during that wildfire smoke event. So now I'm going to talk about the research that I did. This was at Dalhousie University back in 2011. And I got a call just out of the blue from Professor Paul Palmer, who's at the University of Edinburgh. And he explained that he was going to be managing this international study that was going to be based in Halifax. And he was looking for somebody who did air quality research, somebody who sampled particulate matter on the ground. And he just word of mouth, he heard about me and he said, would you like to be in this on this project? And I thought about it for a nanosecond and said yes. So that's how it came about, just complete serendipity. So the study itself is called Quantifying the Impacts of Boreal Forest Fires on Tropospheric Oxidants over the Atlantic using Aircraft and Satellites. The aircraft was the UK government's atmospheric research aircraft, and it was actually used in 2010 to look at the volcanic aerosols from that unpronounceable volcano in Iceland. I don't know whether you remember that. And it's grounded a lot of the aircraft in Europe for a few days, if not a week. Okay, so we use that aircraft. So I was doing the ground-based monitoring as part of this study. And the main objectives were to identify and apportion the major sources driving the temporal variability of PM 2.5 in Halifax. Of course, with a special focus on the boreal wildfire smoke. And it was also used to validate atmospheric composition forecast models. So what they did was run a forecast model to then say to the aircraft, hey, there's smoke over here, this is where we'd like you to fly. But they wanted to validate that model. So they'd run it for the ground station, and then I would send them my data, and then they could see how well it matched up. All right, so the sampling site was on the roof of a building at Dalhousie University in Halifax. And Halifax is a port city. You get a lot of cruise ships. There's a lot of commercial container ships as well as military as well, plus pleasure craft. And that will be important later when you see the source apportionment data. So there were 45 consecutive days of sampling. Within those 45 days, the aircraft measurements were also occurring as well. I measured trace gas species and size resolved particulate mass and number, and also the chemical speciation. And if you suffer from insomnia, there's a few papers that you can read all about it. Okay, the instrumentation that we used. Oh, and by the way, I had about 2 weeks to set this up. So we built a little deck, grabbed in instruments, borrowed instruments, and made it happen. So we used the Thermo Partisol 2025, and that's the Federal Reference Method instrument for sampling and measuring PM 2.5. So pretty much everything is compared with that instrument. And that one had a Teflon filter inside it. I borrowed a magnetometer. This measures black carbon. So remember that black carbon that was in that droplet. All right. And then 2 other samplers. These are called ChemCons. And we had a pre-fired quartz filter for collecting organic matter and a nylon filter for collecting anions and cations. I also obtained the organic matter data from Environment Climate Change Canada's aerosol chemical speciation monitor as well. Because we're handling very small concentrations of PM 2.5, although that filter had a lot on it, that's from an indoor residence with a leaky wood stove. We handled the filters in a clean room. And to get the mass of the filter, we weighed it on a 6 decimal place balance before and after sampling. And that gives you the mass and you know the flow rate. So you've got mass per meter cubed. Okay, so we've got the 3 filters. We've got the Teflon filter there. And that is where we obtained the mass by gravimetric weighing. We also analyzed 33 elements, and that was via X-ray fluorescence and inductively coupled plasma mass spectrometer. And that was done in my former lab at Dalhousie University. We had a nylon filter that we extracted in type 1 ultra pure water, and that extracted the anions and cations. Those are the salts that you'd find in the aerosol. And that was analyzed again by ion chromatography in my former lab. Then the quartz filter was sent to the University of Montana for some special analysis for a compound called levoglucosan. So it's first extracted in solvent, then derivatized, and then analyzed by gas chromatography mass spectrometry. And then for the black carbon, we simply took the 24-hour average and also for the organic matter. So all of that data was then placed into the US EPA positive matrix factorization model version 3. It's now a version 5, and it's a multivariate least squares model, and it doesn't allow any negative mass contributions because that makes no sense at all. So hence it's positive matrix factorization. Okay, now for the model, or for you to understand what the model is telling you, you need to have a chemical marker or a chemical fingerprint of the source. So in terms of wood smoke, you have sugar in the sap or maple syrup, and when it burns, it creates a series of sugar anhydrides, and the most abundant of which is levoglucosan, and that is an excellent marker for the wood smoke. And potassium is also a really good marker for wildfire smoke as well. So if you
Keep going, I'm going to plug it in.
so potassium is a really good marker for the wood smoke. So if you see those 2 together, that's good identification that you see in the wildfire smoke. Cool. Okay.
Keep going, I'm going to have to run and get the other end of this.
Okay.
Right back.
Can I close this?
Close that view.
Yeah. Okay, great. There we go. So when you run the model, there's a number of QA/QC checks that you can do on the model. There's also some robust bootstrapping statistics that you can compare as well, but in the interest of time, I didn't want to show those. But the main QA/QC that you look at, first of all, is the observed PM 2.5 mass with the model's predicted PM 2.5 mass. As you can see, they're in good agreement. And then what you can do, you can go through every chemical species and again look at the observed concentration versus the predicted. And this is nearly a one-to-one relationship, excellent correlation. So I'm really confident, especially for nitrate, that the model is working extremely well. Okay, so now on to the chemical markers. So this is what the model will give you. It will give you a source factor profile, okay, of all the chemical species. And what it's showing is that for levoglukosine, this is levoglukosine from every single sample, it's saying nearly 100% of that levoglukosine is associated with the source factor. Now we're going to name that source factor in a moment. We're going to give it a name of the source. So the model has no idea what it is. Oops, there we go, gave it away. You know what it's going to be anyway. And there's our friend potassium. So the two things that are really good markers for wildfire smoke found in those filter samples. Okay. So you can name it. You can name it wood smoke, wildfire smoke, or smoke, whatever you like. Okay. In a similar vein, here's another source factor profile. You can see there's no levoglukosine whatsoever. Okay, but there's high abundance of silica, iron, and aluminum. And they're the most common elements in the Earth's crust. So you can call that surface dust or superficial dust, windblown dust, resuspended dust. It's all the same thing. Okay. Now, in the interest of time, I'm not going to go through every source factor profile. Okay, so what you can end up with is this time series plot with the 45 days of sampling. The observed PM2.5 masses, the dashed lines, and then the bars are obviously the source apportionment for that particular mass based on the sources. So you can see here there are 8 sources: the surface dust, the LRT is long-range transport, and pollution, that's coal and industry, and the chemical marker for coal is selenium. So the selenium popped up in our model. We've got the wood smoke, we've got long-range transport of pollution marine mixture. So that's air masses that came from the Northeast United States were full of long-range transport pollution, which then mixed with the sea salt en route to Halifax because the air mass crosses the ocean. Then we've got ship emissions. I already mentioned the ship emissions are in Halifax Harbour. And you may not know, but nickel and vanadium is in the oil, the gearbox oil of ship emissions, and it gets into the combustion gases, and it showers nickel and vanadium all over a port city. So there are no mines for nickel or vanadium, but you see it in the particulate matter quite readily. Then we've got long-range transport pollution, ammonium sulfate. The ammonia comes from agriculture, and the sulfate comes from the burning of fossil fuels with sulfur in it, so diesel fuel, for example. We've got gasoline and tire wear, and the model, and from my knowledge, I couldn't tease them apart. They're basically the same source, right? But the emissions plus the tire wear happening at the same time. It's the same for vehicle emissions as well. Now, in some studies with more data and maybe a better detection limit, I might have been able to tease those two apart, but I couldn't in this particular study. Okay, so you can see the model works really well for the very low concentrations, and these are incredibly low. I mean, as I mentioned, the air in this room is probably around 2 micrograms per meter cube. So we're down here, which is incredible that A, we could measure the mass, and B, that the model is actually matching that mass. Then for the higher episode, I say an episode, it's still pretty clean air, but the source apportionment works pretty well. So what evidence can we use to identify the wood smoke in our sample? So we've got, again, our air mass back trajectory. This time it's overlaid on a fire hotspot map. So you can see where that air mass back trajectory is crossed over the fires en route to Halifax. So this is a really good tool to helping us understand what we're seeing from our model. And then what you can do, you can take those air mass back trajectories for the 45 days of sampling and place them on one map. So we like to call this the spaghetti monster. And then you can divide them up into source regions. can divide them up into various source regions. So we've got 40.2% from the marine environment. So you'd expect those air mass back trajectories to just contain sea salt. We've got the red, which is 16.3%. These are air mass back trajectories that tracked across the Northeast United States, picking up air pollution from the Ohio Valley, the I-95 corridor, and then crossing the ocean to Halifax. And then we've got 27.2% of the air mass back trajectories came from southern Ontario, again, entraining air pollution from there and bringing it to Halifax. And then the dark blue, 16.3%, these are air mass back trajectories from northern Canada, where we get pristine air, very clean air. So you'd expect to see very low PM2.5 concentrations. So you can use the spaghetti monster to help explain the features in our time series plot. So for the very low concentration days, we saw indeed that the air mass came from northern Canada. It's a very clean source region, characterized by low PM2.5. And it didn't track across any wildfires. And then we've got another low PM2.5 day. And again, the air mass came from the ocean, so no wildfires, quite clean, just had marine salt and some ship emission mixed in with it. And then the largest wood smoke day on the 31st of July, the air mass actually tracked across wildfire on Newfoundland and Cape Breton as well, en route to Halifax. So that's where we assume this wood smoke came from that we saw in our model. And then there was two things happening here. There's an air pollution event. I say event, it's still very low, but you can see it's a spike compared to the rest of the time series, dominated by ammonium sulfate, but we also had wildfire smoke in there as well. And this was due to a wildfire in Ontario. So we can use the true color satellite imagery from NASA Aqua MODIS to observe this river of smoke from southern Ontario, passing down all the way, impacting Halifax. So again, good evidence to support what we're seeing from the modeling. You can also use dispersion models. So this was run by one of my students in my lab, and this is FlexPart. And FlexPart was used to model the radionuclides from the Chernobyl disaster in '86, and it's still being used today. An interesting feature here was that the wildfire smoke, it dipped down over the Northeast US, picking up all of that air pollution, and then advecting it to Halifax. And that's what we're seeing here. And then FlexPart again, you can do it in the vertical. And so if the air mass or the wildfire smoke was up at 8 kilometers, it's not going to impact the ground. But the model is confirming that, yes, that wildfire smoke and long-range transport pollution did indeed impact the ground. In fact, the concentrations are around between 1 and 8, which is exactly what the model was predicting. So, it just shows how accurate some of the models can be. There's the concentrations there again. So you can see it's about between 2, 4. So again, very, very similar to what we're seeing in the FlexPart model. Okay, so then finally what you end up with is a pie chart, which is the average of all of the measurements over the and modeling over the 45 days. And we've got the mass concentration in micrograms per meter cubed, and we've got the percent relative contribution as well to that total PM2.5 mass averaged over the 45 days. So for wood smoke, we get this very low concentration, 0.61 micrograms per meter cubed. Remember, in this room, it would be about 2 micrograms per meter cubed. Now, if I did the same approach during the wildfire episode that we saw in June, I would say that wood smoke would be up at 200 or 250 micrograms per meter cubed if we were able to run the same sampling and modeling approach. What also is a salient feature here is that if you add up tot up the average of the long-range transport, we're at 69%. Now, that may come as a surprise, but Nova Scotia is known as the tailpipe of North America. Gets all of that air pollution from the Northeast US passing across the ocean and impacting Halifax. 10% ship emissions, that's no surprise. We've got a lot of ships in Halifax. We've got 6% surface dust, we've got 1% from diesel and 3% from gasoline vehicles. And that's about the right ratio that you'd see for those vehicles in the town. So if you were an air quality manager, the only things you could really manage in the city are the ship emissions, the gasoline and diesel. The long range transport and wood smoke, wildfire smoke, you can't manage with local policy, okay? But you can with national and international policy. So there's actual policy groups working on transboundary air pollution between the US and Canada. Okay. All right, so that's the end of the research, but let's think of some other applications of PMF. It's not just for air quality. You can use it for any environmental sample. You can use it for water, you can use it for contaminated land, and it's been used for those situations many, many times. You can also apportion gas species. So if you have lots of VOC species, say gasoline vapors, dry cleaning, you name it, if you measure the total VOC and you've got those VOC species and you run the model, you can apportion those sources to the total VOC that you're seeing at a receptor. You can actually use it as an aid to air permit applications and compliance, and that's pretty much my life now, where an emitter submits a permit and they have to remain in compliance. So if a big emitter of air pollution, say a chimney stack, you can do the sampling and run the model, and you can say, hey, this chimney stack is only contributing X amount to the downwind receptor. So it's very useful for that. You can better understand the wildfire smoke and their impact on downwind receptors, so ecosystems and populations. You can provide insight to inform policy, as I mentioned, local and transboundary emission sources. It can be used to provide exposure data for health effects studies. And it can be used to augment visibility studies. And there are 52 sampling sites in the US where they look at visibility, and they use exactly the same methods that I've used in this project. They only sample every 6th day because it's so labor intensive, they can't do it on a daily basis. And as I mentioned before, the approach can be used to validate and constrain atmospheric models. It can also be used to constrain air dispersion regulatory models such as AirMod. So AirMod is approximately 2 times the error is about 2 times. So if you run these models, you can help constrain the error within AirMod. And CalPUF is a long-range transport model. And I mentioned as well that you can validate the aircraft and the satellite observations as well. So I'd like to leave it there, but I'd like to acknowledge the team that helped with the study, especially Mark Harrington, who actually works for the European Centre for Medium Range Weather Forecasting, and he supplied some of those animations. That's his job now, so it's interesting that we collaborated on this project. I'd like to acknowledge Paul Palmer, who funded the project from the University of Edinburgh. I'd like to acknowledge Nova Scotia Environment, who supplied weather data as well as personnel to help with the project. And I'd like to acknowledge Environment and Climate Change Canada for all of their help, and also for obtaining the organic matter data for the project. So I'd like to thank you for listening, and I welcome any questions.
Well, if I stop sharing the screen, I think I can have you on camera, so these people can see while you're answering questions.
Okay.
If you need to go back to the slides, we'll figure that out. But let me just do that real quick. Okay, let's go ahead.
Okay. See my face. Oh, that's terrible. Yeah, definitely a face for radio. Any questions? Sure.
I'm curious, do these patterns change seasonally? And If so, like, do you see the size and the frequency of these wildfires, like the increasing size and frequency of these wildfires changing historic wind patterns, like the prevailing wind?
I'm not so sure about the prevailing wind, but it's mainly the heat that's been the big driver of the changes. So the fire seasons are starting earlier and they're lasting longer and they're making the fires more intense. So sure, during the fire season, I will be able to pick up the wildfire smoke, no problem. Because when the fire season's over and you have snow on the ground, then you know, you won't be able to sample the fire smoke and you won't see it in the model. Yeah.
And I was just, so. Why get fire, forest fire and walk it down, else than the critic, like, is there both?
I think because you're so close to the campfire, you're getting the smell of the sugar anhydrides, that sweet smell. But you're so close, you're right on top of it. Whereas the wildfire smoke, it's had chance to disperse, so you're not getting. Did you say smell?
Yeah.
Yeah, you're not smelling.
Smell versus like the burn toxic smell.
Yeah, it could also be due to the heat as well, and not degradation, the combustion of the materials and the chemicals in there might change compared with the wildfire smoke, compared with the campfire smoke. It might have wet wood, so the combustion products might be different. Yeah. I'm trying to convince myself of that, but it seems like a good argument.
Thanks for your talk. So you mentioned briefly that you're now kind of on the regulatory end of things, or
Yes,
working with compliance.
yes,
And so I guess I have kind of a bigger question, not so much about this research project, but more about what you're doing now. And how it
yes.
relates to the wildfire smoke. Does the presence of that smoke complicate the regulation of local air pollution sources, like when we're talking about permitting? Like, do they use it to maybe justify their level of pollution?
Right.
versus the level of pollution that we're getting from the wildfire? Like,
Sure.
does that become kind of a, I don't know, rhetorical problem as we're talking about what we need to regulate? Does that make sense?
It does, and it does complicate the picture for sure. Because typically the way the permit works is you measure the air quality locally, and there are standards for that local air quality, and it might be below the standard and they call that an attainment area, or above that standard and that's a non-attainment area. And depending on whether you're in an attainment area or non-attainment, you'll apply for a certain type of permit. Now, of course, with wildfires, it might bump that level up a bit into non-attainment. It means you've got to get a different type of permit, which it is very restrictive on the source of the air pollution from that facility. I saw my face and it put me off. So I think that answers your question, I think.
Yeah, I mean, I'm just, if you are bumped into non-attainment,
Yeah,
is that changing the responsibility of the polluters in the region, right? That
Yeah,
now they're going to
yeah.
comply with something much more strict.
Definitely. They may all have to reapply for different permits. They may have to put on retrofitted air pollution control systems. They may even need to close down that emission source and put in a new, more efficient emission source. So it opens up a whole mixed bag of things. Okay. Sure.
Since the fire probably caused the ecological disruption in that ecosystem, has there been any talks about how many species of terrestrial mammals have been displaced?
I don't know, 'cause it's not my area, but of course, that's a great concern and a great question. But I don't know, unfortunately. I'm sure there's a huge amount of research being done on that, though. Yeah, yeah. Sorry,
So-
go ahead.
This is all fascinating, and the fact that we're able to track things and model them as well as we can is really quite amazing. And the question I have is that the research campaign you talked about was a decade ago.
Yes.
I'm sure it costs a lot to mount that array of equipment, 45 days.
Yes.
But given what we're facing, I'm curious as to whether major metropolitan areas are thinking they need to actually have this kind of monitoring to be able to track what's coming, where it's coming from, and what potential.
Yes.
Has there been an attempt to expand the use of that kind of array of equipment to really have much better sense of the broader geographic region?
Yes, in fact, most cities have the sampling equipment and they do the chemical speciation, but they use a different type of model. They use like a recipe and they just say, if you've got this number of sulfate atoms and you've got this number of ammonia atoms, you're going to have this much ammonium sulfate. But they don't do wood smoke. They don't look for wood smoke at all. They're looking more for surface dust and vehicle emissions, ship emissions. So, but it would only take them, to do some extra analysis for, say, levoglucosan, and then to run this model instead. Then they could get at the wildfire smoke. But there are those sampling stations, probably in Baltimore. I've seen a big station on things to Baltimore, Washington Parkway. There's one there. But they do exist. In fact, there's about 52, 62 across the nation.
I imagine it this summer, you might get cold.
I hope so.
I guess, look, from your talk, one takeaway is Halifax is a pretty clean place, since all the pollution seems to come blown in on the wind. That's
Yeah.
kind of my takeaway.
Yes,
Depends on where the wind blows.
yeah,
I was wondering what you think something like that would look like here with much more, indigenous pollution, I guess.
absolutely. Yeah, those
Less
numbers,
dependent on wind or,
the vehicles, everything would be much, much greater. And as I mentioned, during that wildfire event, the wood smoke contribution, it could be up in 200 micrograms per meter cube, which is like living in Delhi or, Beijing. Compared to Halifax, which was down at 0.61 micrograms per meter cube. So yeah, Halifax is a pretty clean environment to live in for sure.
so it seems like Halifax, the wind never does you any favors.
It
Could it be
brings-
opposite, like here, where the wind is actually could help you out on some
Yeah,
days, it actually makes
yeah.
it better?
Yeah, definitely. We see some bad ozone days, which is a secondary pollutant, which is caused from the primary emissions in the northeast US, and they come up over Nova Scotia. Yeah, we see some fog. I took a photograph of a look off over the Annapolis Valley, and there was some tourists, and all the smog was just filling the valley. You couldn't see anything, and the kids like, "Where's the valley, Mom?" And it ruined their day. Thought they could take some nice photographs, but the smog which came from this region obliterated that photograph. Yeah.
Okay, we're just about 12:50, so if somebody has a really quick question, jump in and ask it.
During this summer, I was working at College Park doing anthropology research.
Okay.
And the PhD student and the director of the program spoke about it and was like giving warnings of us wanting to stay in the house more.
Yeah.
Until it passes over. I was thinking about this during the summer. In reference to the precipitation cycle, should we be more concerned when it rains after these events happen?
No, actually the opposite. 'Cause the rain scrubs the atmosphere of particles. So when it rains, it cleans the air from the particular point of view. Yeah.
Yes, but don't go particle, never mind, okay.
Yeah. Yeah.
Thanks very much to our speaker. We're gonna have to, if you want to talk briefly on the way out. Sorry for the issues.
No problem. We got through it.
Yeah.